Good morning to everyone. Today we will be discussing about tailored modeling solutions in Alpha Bridge, and we will look into the different modeling techniques. My name is Moal Gidey. I'm a BIM Bridge Research Engineer at Allplan. I have joined the company 2+ years ago. We have been working on different modeling techniques so far, and which is, of course, the topic of today to discuss all these different techniques that we have. So before we go in detail to each one of them, let's just have an overview to the modeling techniques that we have. As you can see shared in the slide, we have few modeling techniques. One of them is the axis-based modeling, which was the classic modeling technique in Alpine Bridge. This was really an important milestone because it allowed users or designers or engineers to model a bridge parametrically. So in a sense, everything was easier to adjust, or it was quite easy to introduce change. Then we had the Link-Girder Modeling, where we can place an element between two spatial points. So in a sense, when you have a girder, you want to place this same girder between two piers, for example, so you can use this kind of modeling technique. But of course, this is not limited to just girders. You can also use it for trusses or cables in cable-stayed bridge, or other elements for that matter. Then the latest modeling technique that we have is the Free-Parametric Modeling, which is quite innovative because it allows users to freely shape an element. Of course, everything is parametric, but you can adjust the element as required. And of course, also add or do Boolean operations in a sense to add two objects together, subtract them, or do some other operations. But the end goal is to have parametrically defined shape or freely defined parametric shape. So you can easily introduce change as well. So all these three techniques we'll be discussing today in detail, and we'll look into some examples or use case scenarios, and we will dive into that. But before I go, just quick reminder here that all these techniques are of course parametric design approach. So all these have that principle inside, so you can introduce any change at any point in the modeling. So let's start with the axis-based modeling, which is the classic one. So the axis-based modeling, the idea or like the technique behind is that you have a cross-section that you have defined, and you use this cross-section to extrude along an alignment. So for example, we have an alignment, and this alignment we can extrude a cross-section, a hollow box cross-section, for example, and we can extrude this cross-section along this alignment. So in a sense, we have the model or the element. This kind of approach is quite useful when, of course, when you want to have better change management. That is when you want to have a parametric model. So if you want to change the alignment, for example, and you can easily do that. And once you change the alignment, the whole element or the whole deck will also move or will also change. This is because the element or the deck is based on two things, which are the axis and the cross section. So once you introduce change at any point or at any of these two things, the resulting or the intent will also change. So that's the advantage for the axis-based modeling. Secondly, it's quite useful when you want to define geometries accurately. So in a sense, we have here, as you can see, the girder, and we want to change or we want to introduce some variations to the girder deck height. So you can see that we can easily do this if you have this kind of modeling technique where we have axis-based modeling. So in this sense, what we can do is like we can introduce a parameter for the height of the cross section for the girder. Then this parameter can change along the alignment based on the station of the alignment. So as shown in the table, we have from stations from 0 to 155, and on this we have different values for the height of the deck girder. So this changes, and this is changed, and in a sense, we're defined the geometry accurately. Lastly, it also allows you to capture really complex shapes because, like I said, it's a parametric solution, a parametric approach, and in that we have a set of parameters or inputs which control the final design output. And these inputs can be, of course, mathematically defined or attached to some other behavior. So the final shape could also be quite complex shape, which is really hard to model freely or using the other modeling techniques. So that's why using this axis-based modeling can be useful for really complex shapes. So to show you an example of such an approach or such a project, we have one example here. This is the arch bridge, and I'm going to share the product and the presentation. Here, as you can see, we have Alpine Bridge. This is the product. Just to give you a quick overview of the product, here on the left side we have the navigation area, so where we can navigate through the different components. For example, we have an axis, so you can navigate to the axis here. If you have an axis elements, you can go inside the axis. Cross section also applies the same thing, and also for the members, maybe the girder, pier, and so on. You have that. Of course, you also have other tabs where you can use them for navigation and also for creating components or elements. And at the top, we have also a few functionalities or tools which will allow you also to do the creation or the navigation as well. So you can create an axis here or create a cross section here and so on for the 3D modeling as well. So the example that we want to see is the arch bridge, which was modeled using an axis. So this is based on the axis-based modeling. So we will be loading the project to see. So as you can see, this is the bridge project, and we have two decks at the top, and which has some super elevation, and we have an arch here, few arches, like 4 in the first span and 4 in the second span, and basically this is the project. So for this kind of projects, usually it's quite hard to define the alignment or the arch or the curvature of an arch without using any axis-based modeling. So if you're using any other technique, or for example, freely modeling it on any 3D software, 3D CAD or BIM, it's quite hard to define the curvature. But with the help of the axis-based modeling, we can easily do that, because these are just, as you can see, the red parts, these are just the axis. So if I try to hide this object, as you can see, these are basically, this red part is just an axis. So this is just basically an axis. So we can easily define such axes or such curvatures, and once we have them, we can just add the cross section and extrude it along that area. So that's how basically we can create the curvature of the arch. So to show you here in the navigation tree, as you can see, if you click on the axis, we have a set of axes here. And just to go in, so this one is for the top of the deck, and we have for the arch also the same thing basically. But if you go to the profile, you can see we have the curvature that we wanted to achieve. So the same also applies to the other curvatures as well. So once we have the axis defined, we come to the cross section. In the cross section, we can see this one doesn't have any variations in the cross section wise, but of course, if you have any variations, so you can basically define that also here in the cross section. So here, this is the cross section. So we have the arc, but for example, we want to do the variations here on the deck. Here, as you can see, we have a lot of cross sections, a lot of boundaries, and we can, of course, navigate this and play around here and change them. So we have, as you can see, we have a parametric cross section as well. So once we created the cross section, depending if whether we want to add variations to the cross section or not, we can create variations. So for example, we have a variations for the slope angle here. So this would vary it with the slope angle. So we have from 0 to 262. So we have the slope here. So this would vary it from here, from the station 0 till the end. So we can have a variation. Of course, this doesn't necessarily have to be applied for the deck. You can also apply it for any other cross sections as well. Then once we have the cross section and the variation defined, we can create basically the geometry. So you can see we have the geometry for this one defined, and also for the arches, we have this one also defined. Basically, we can do that. Also, the same applies for the pier. So the logic behind, or the technique or the principle behind this axis-based modeling was, we define an axis, and this axis could have, of course, profiles and plans, and of course, variations on that. And then you define the cross section which you want to use on this axis. Then you can apply also variations to the cross section. So this was the first example. The second example that I want to share was inspired by the Lucky Knot Bridge. This is from China, which was designed by Next Architects. I want to share this example because it really shows how we can capture really complex shapes. So this was the advantages of axis-based modeling that we discussed a few slides ago. So to show you this bridge project, I'm going to go back to the product once again and load that project. So with the axis-based modeling, we said, of course, our starting point or the main principle is with the axis. So we have to create an axis. So here you can see we have created an axis. We have one axis here. And first, just to show you the bridge project, so we have deck here, which goes and splits into two, and also comes back again here, joins back again these two decks, and goes into the end. Of course, if you see from the side, when it splits, it has like this sine and cosine functions. This one has a sine and the other one has a cosine functions with different wavelengths and with different cycles. But basically the concept here is that you can have an axis or an alignment which has different shapes, and based on these different shapes we can introduce or we can add the cross section which will be extruded along that area. So to show you, here we have an axis. So the axes are basically, they are just straight two axes. Axis 1 is straight like this and axis 2 is straight like that. So basically we have an axis, a straight an axis from here till the end one straight axis. But how we did or how we introduced these variations or this kind of shape is that first we created a cross section here, simple rectangular cross section. This is just to show you the principle that you can also add any cross sections here or easily swap the cross sections. So I'm going to change this girder here. You can see I'm going to change this cross section from deck one to a rectangle one and apply this cross section. And this would be applied to every station that we have. And you can see we have a straight deck. So this was basically the straight line that we have, the axis that we had. So this was, as you can see, this is the second one, which was the correct cross section, but this is the rectangular cross section that we created, which will be just straight because the axis is straight. But if I undo, everything here, we are using this cross section, the deck cross section, which has few variables. So as you can see, we have few variables such as the Z. This is the Z offset and offset from this position. So as you can see, this is Z offset and offset from this position. So it could be few offset or few meters or millimeters away from the center. Then we have a spacing. The spacing is between these two. How far do you want them? Because as you can see, the objective was, okay, we can have them together here and we can have them with some distance apart from each other. So we wanted to achieve that. Then we have also the deck height. So this is also for this one. The second, this deck height, if I move it, you can see it's moving up and down. So this will control this part, because when these two decks or when these two sides of the decks are joining together, we would not want to have the center any kind of height or any kind of barrier. And finally, we also have the width, so which controls the width of the width of each side of the deck. Basically, once we have defined the cross section and the variables, we can, here as you can see, we can have variations. So I want to control the Z offset. The Z offset basically meaning this part. So how far, if I move here and if I show you here, so how far from the center should this be up? So how far should it be? So here it's at 0, here it's a few meters up. So how far do you want that to be? So that's controlled by this Z offset. So what we applied here is, for this Z offset, we applied a variation. So if I see the variation, so this is the variation as shown here. This is using a formula called sine function. So we're using that. If I just remove this one and say, for example, just 5 meters and recalculate everything, you can see it will be 5 meters from the axis, and it will be placed like that. But for us, for our case, we want to apply a sine function like this, and it will have a sine kind of wave as shown here. So basically, we can apply an axis and cross section to create different geometries and navigate through that, or manipulate the shape, of course, and also the cross section to create different geometries or to have a different design output. Going back to the slide, we saw this for the axis-based modeling, where the focus was on creating an axis and on providing a right cross-section. Then by applying a variations to the cross-section, we can create different shapes and we can have different outputs. The second approach or modeling technique that can be used in Alpine Bridge is the Link-Girder modeling. The concept or the idea behind Link-Girder modeling is we have an element or an object or a template defined, and this template can be placed between two spatial points. So spatial points meaning here there can be two 3D reference points between, for example, we have two 3D reference points here, so we can place them. Or it could also be just an offset from an axis or station in an axis with some offset on it and placed also to the other one. So basically it's between two different spatial points. Depending how you define these spatial points, it could be from axis or it could just be based on the cross section that you have. The use case for this would be, or before I jump to the use case, just to show you here a practice or the workflow practice. So here, for example, we created a girder as a template, and this girder is the object that we want to place. So this is just a girder to show an example, but it could be any element. So the concept is once you have an element defined, you can use this element and place it between two different points. So as you can see, we are placing it between two, or like between the pier and the abutment, because this is a girder. But this applies also for the other elements or in other different use cases as well. And the same, of course, once you have it defined, you can copy it multiple times and you can play around with the naming, and you can, of course, place it accordingly so to be done. So maybe you can see here why we need, or what would be the advantage or the use case scenarios for this kind of approach or for this kind of modeling. One of the use case scenarios would be when you have repetitive components or elements. Like we have seen in the previous slide, we had the girder. The girder is quite repetitive. In that case, it could have different lengths, but the shape was quite the same. So in that case, we want to use Link-Girder based modeling. Also, as you can see on the right side, we can also use this kind of approach when we have, for example, elements or components such as here, where we want to place them repetitively. These are like cables. We want to place them. This is a pedestrian bridge, so we want to cable state pedestrian bridge, and we want to place these cables or this kind of supports. And these are repetitive elements, as you can see. So for that, we just want to create it once as a component and just copy paste that and place it accordingly so it will be placed. And of course, if we're talking, if it's just one element, it means it is a templatized element. So it could be one template that you create for this element, and then once you have it created, and you can use it, as you can see, to place it accordingly. This is to show you that it doesn't necessarily have to be a straight element, like from this like straight object or element like we have here, or like we had in the girder. It could be any shaped, which has, like, as you can see, shape which is variation, which has a few variations in terms of the height, in terms of the width of the panels here. So you can have different types of shapes as well. Regardless, it is templatized once, then you can use it multiple times. For this, the use case example would be, one of this one would be for the cable stayed bridge. This one I will also demonstrate in the product. I will show you the project. Here we have the cable stayed bridge. Here, as you can see, we have a cable stayed bridge where we started with the axis-based modeling, where we added the girder here, the whole girder, and we have the whole girder here, which was modeled using an axis-based modeling. Then we have also the pier here, and this pier is also modeled in such case using a cross section. But for the cables here that we have a lot of cables here, and for that, first we need to create a cable template or a cable object. And we have created that cable object, so it should be like this. So it's a set of diameter and a set of cross section defined already, and set everything properly at the template level. Then once you have the template here, and you can just place the template or place this template by dragging and dropping between these two elements. So the advantage, like I said before, is these are quite repetitive elements, so we don't have to recreate them. The advantage making them like this or making them in template is that, so here you can see this is, for example, a rectangle circular shape. And if you want to change it, for example, to a rectangular shape, so I'm just going to change it to a rectangular shape with a diameter of 0.2, 0.2. So I have created a rectangular shape, as you can see here, and I want to change all these cables, as you can see, which are circular in shape. I want to change all these cables. So if I had to do them manually one by one, it would be quite a lot of work. But since I have a template, so I have these templates, I'll just go to the cross section here and change from this cable to a rectangle, and this will be applied for the whole element basically. So if we recalculate and go back here, you can see now it has become rectangular shaped. And if you go also to the geometry here, you can see it has become rectangular shaped. So we were able to do that, or we were able to introduce this change and effectively and efficiently achieve that because of the template that we have. So this would be the advantage of templatizing. Another use case example that we can have a look inside this area is also for the truss bridge. So here we have also, as you can see, components which are quite repetitive, starting from this top or like the main arch or the main parts to the truss parts that we have. So we can also use or achieve this kind of model using Link-Girder Modeling. To show you also this or to demonstrate this one, you can also open this project, load it, and have the project as shown. So here we can notice that we have a link girder here. Basically, this is the same kind of thing where we have template defined. And once we have the template defined, okay, we start placing the elements. So we start placing here, and we can also go on and see, you can see we have placed quite a lot of trusses, but basically all these elements are placed because we were able to define this as a template. Like I said, if you want to change the diameter of this, you can easily change that. You don't have to select everything. You just come here. For example, let's make it a bit smaller. So we have in the cross section here, and the cross section we have the section girder, this part, this is the main part, and we have also the section truss. So for this one, to introduce, for example, a change to the diameter. So this is the radius. So for that, we need to define a variable called radius r, and that we can easily introduce that change. So we can introduce this radius r, and this could be 15, 0.15, and we can recalculate everything. So everything is the same as before. But if we want to change that, like I said before, we can come here, we can change the radius, which was 0.15, we can make it 0.25, for example, and this would be quite thick, but it will be shown here. As you can see, this is quite thick and everything's here, but it can be shown like that. So basically we can, like I said before, we can easily add or introduce the change that we want to achieve by just changing the template, and from that template everything could change. So you can see we have changed everything. So this is because we have a link-girder approach where the main focus is on creating a template, and once the template or the object is created, we start placing it between two different spatial points, between two different 3D points, then basically we have the model. The third and the latest modeling approach in Alpine Bridge is the free-parametric modeling. This, as defined previously or at the beginning, is a parametric approach or a parametric modeling technique where elements can be parametrically shaped or freely shaped. In a sense, we have, for example, a box, as you can see, shaped or a cuboid shaped, and we introduce a change by extruding or subtracting circular or cylindrical part. Then once we did that, we were able to add or we were able to modify the girder by changing the variations and by adding the variables or by changing the variations basically. So here the objective is that you can introduce the change at any point, but of course the operations that you did, such as like the extrusion or such as the Boolean operation or the subtraction operation that we did or we are doing now, will stay parametrically in relation to the object. So for example, if you change the height, that operation will stay in that position. If you change the thickness, because we were doing it half of the thickness of the shape, you can also see the subtraction of that shape till the half of the thickness. So the use case for this kind of approach or for this kind of modeling would be, of course, the first one would be when we want to have a templatized objects. So templatized in a sense, before when we say templatized, we have one template or based from one cross section, one template. But this one you could also do that and also maybe take it a step further where we can have a combination of different objects. So that would be kind of a template ones, and by using different approaches such as partial import and export, you can for example for this kind of element that we have, you want to use maybe multiple times. This was created using the free parametric modeling, so we can use this, create it once, use it, or save it as a partial TCL and use it in different projects. And basically we are templatizing a lot of operations which are done here, such as the Boolean operations here and also the variations in height and so on and so on. So basically all that would be abstracted into one object, and this object could be used as partial TCL in different projects. Of course, the second use case or the second obvious use case scenario would be the arbitrary shapes. So when you have a cross section defined, when you have a section based on a cross section, usually you have the shapes defined based on the cross section. So it would be kind of an arbitrary cross sections or arbitrary shapes. When we say non-arbitrary shapes, here, for example, we have this kind of arbitrary shape, but we want to add some, I don't know, some holes on the sides and some other things here. Also, maybe add some object on the top or on the side and all these things. Basically, this non-arbitrary shape can be defined because we are able to add different operations on top of this, and of course, manipulate it using different objects, also the same cross-section. And the third use case or use case scenario or advantage to the approach is the better model integration. Here, when we say better model integration, when we have, of course, a parametric approach, everything is quite integrated. So when you move the alignment, as we've seen in the previous slides, the whole deck also moves all along. So this is the model integration. But to this, the free parametric approach, what's really achieved was like a even more enhanced model integration, in a sense that when you add an object and place it maybe at the edge here, or place it, for example, at the edge here, and when you change a bit the thickness, this model or this object will have a thickness which is narrower, so this edge point would be here. If that's the case, then the object that we place based on this edge point would also move to that new location. So you can see all this kind of integration of models because we have this free parametric approach. Better would be demonstrated in a project example that we have already included in the product. This is the integral bridge, which is already available in the product. So if you go to the product, and in the product you go to the startup window. If you restart this startup window, you can see this the example that we will see. So here, the integral bridge, we have here the description and the project obviously here, but we also have the YouTube link video where you can see how the whole bridge was modeled. For now, I just want to show or demonstrate a few things to the idea behind the free parametric modeling. So in a free parametric modeling, the idea is, okay, we start, of course, we need to have a set of cross sections. So we define different cross sections based on what we want to achieve. So we have, for example, wings, we have side curves like this, and we have the plate defined. So we have basically the cross sections we want to use. So for this part, for this, and so on. So once we have the cross section defined, if you want, you can include the variations here, but for the free parametric modeling, we don't need a variations. We can just start working directly. So we have, for example, in the bodies, we have the template. So we have a template for the box. We have a template for the wing side here. We have the template for the wing here. So all these different templates that we have, we're going to use them, and of course, we want to use this thing and create our object basically. So here we started with the first prism. So this is, as you can see, it's not the whole abutment, but the first prism is just the prism, this part. If I try to reselect this part, only this part or only this area. Why, when we select all the others are selected, is because we have already defined some Boolean operations. So if we go to the Boolean operations, you can see we have added different objects to the dot and also did a subtraction. We did subtract the deck prism from the the wall here, as you can see, we have subtracted this part area, and we were able to achieve that. So if I hide this part, for example, I hide this part. If we hide the deck prism, you can see we have here an operation that we did where we subtracted this area. So what we did was we had a wall deck here at the top, and from the wall, or, no, we had an abutment wall. Sorry, we had an abutment wall, and from the abutment wall, we were able to subtract the prism deck, and for that we have, of course, this subtracted object. But of course, you can also see when we hide this thing, we have also the wing wall, or like the approach for the slab approach here, placed at the top, which is not touching or aligning with the abutment. So if we show all the objects back again, you can see we have the project defined here. So this was for the abutment, and if you click on the other objects, you can see the information here, and they are not visible there because we have selected auxiliary. And if I turn the auxiliary off and try to select prism 8 again, and we can see it. Now it's hidden, but we can also see that. So we were able to define that, and once we have defined the templates, and from the templates we place the objects, and from that we of course create the shape. So what I want to show here is that, or what I want to demonstrate here is that, so this is based on the free parametric modeling, where of course this object that we have created, this one for example, has different Boolean operations and so on and so on. And what we want to do is we want to add, or we want to introduce some change, and I want to demonstrate, or like we want to demonstrate how everything is properly integrated. So we have a prism, or we have a wall here which is placed at the station 0 for the first wall, and we have the second wall which is abutment 2 prism 1 wall, which was placed at station 20. And if we go here to the axis, we have from station 0 to 20, and I'm just going to make this a bit longer, 30, and I'm going to add this one also to the profile, so to make it a bit longer, so we have a bit longer alignment. And if we come back here to the second wall which we placed it, so this is just the wall, abutment 2 prism 1, this is just the wall, but now it's selected because we have joined the other elements to that wall. So the wall is the parent element. So if you move the wall from station 0 to station 30, recalculate everything, so you can see it moved and it has become a bit longer. So the alignment at the end was here. The alignment at the end was here, as you can see. The alignment here was at the end was here, from which started from 0 here, and it ended at here. As you can see, this is the red part. So this was the station 30. If we click here, you can see that. So this is the station 30. So it moved. So this was possible because, of course, we just changed the parent element, and once we change the parent element, this parent element that we have here, so we can change it back. We changed it from the 30 to 10, for example. So once you change that parent element, or you move this parent element, the other elements which are here, or basically the wing elements and also the foundation parts and so on, because they are joined by the Boolean operation to the parent, they will also adjust accordingly. So this what we are referring when we are saying we have a better model integration through free parametric modeling approach. So this could be the use case scenario. Of course, this free parametric modeling doesn't necessarily have to be applied for bridge components or bridge elements. You can also use it for different elements, such as, I don't know, for infrastructure like tunnels or highways and so on. Or you can even use it for also architectural elements, when you can also create parametric objects which are complex in shape, which are not so easy to define using the traditional modeling or the traditional CAD modeling approach. So with this slide, we're coming to the conclusion, to the final part of our slide. This would be the best of all the modeling. So this is a project that I'm going to share, but before I go and demonstrate the project, just a few things to mention here. So when we say the best of all the modeling, usually we're referring, when you're doing a modeling approach, you don't have to strictly follow to one or the other of the modeling. You can use each of their strengths and model complete project. So for that, or saying that, I'm going to show or demonstrate the project, which has the best of all the modeling approaches. So if you go to the projects that we have here, and this is the last one, which is a precast girder bridge with of course axis-based modeling for the deck and for the superstructure, also for the substructure such as the pier as well. And we're also using here the Free-Parametric Modeling to model the abutments here at the end. And of course, we're also using the Link-Girder to model here the girders that we have here. So here we have a girder. So this girder is placed between an element here, the position here, and till this position at the end here. So to just show or recap everything that we have said so far. So we said when we are working with an axis-based modeling, we need to have an axis. So an axis, as you can see, we have an axis. So this axis would control the whole design intent. So if an axis, for example, here with the radius is of 500, and we can change it maybe to minus 200. So it would move something like that. So the whole project would also align in that order or in that shape. So this would also move in that direction. And once we have the alignment defined, we can of course have different types of axes which are already available in Optimum Bridge, which will allow you to play around and create better shapes or better results. So one of them is the terrain axis. So this terrain axis could be based on the main axis, and from the main axis you can create accompanying axis, so which will follow the main axis. If you change the main axis, the alignment, the terrain axis would also follow that main axis. So we can have that. So once we have the alignment defined, we create the cross section. The cross section, depending on what we want to achieve, it could be a girder, simply defined as this, or it could be an abutment, the shape defined as such. And of course, it could be a wing wall, also define something like this, or also the pies define something like that. So for all these cross sections that we have or we want to use, we can, depending on the use case or what we want to achieve, we can create different variables or variations which will control the cross section. So once we have that, and we have also variations defined. So we have a variation defined for the wing wall height or for the cross frame angle. So we have also cross frames, which I will show. Then based on once we have that, we can of course create the girder, and from the girder you can see we can create, for example, I want to create here the deck. Here we have a concrete deck. This is the equipment deck, this part, as you can see. We can hide this one. And if you click here, equipment deck, and click, we have hidden the equipment deck, and we only have the concrete deck at the top. So this was modeled using the axis-based modeling that we said, okay, we have an alignment, we have a cross section. Based on that, we can extrude that element. And if you try to hide, if you hide this one, also the concrete deck once more, we have the we have the girders. So we say, okay, we have a link girder. In link girder, the first thing is we have to define the girders. We have to define the template. So the template for this is the girder. So we have a girder defined like that. So this girder will be used and placed. So you can see it's placed here. So we have a girder here. This one is the girder here with the height of 44.386. And we have a second girder, for example, this one. If you select the C2 girder 6, we have a height which is quite different. But still the height is quite different. We can also have different variations of the same girder, but basically this is based on this same girder which has this kind of shape but different lengths. So based on that, on this link girder approach, we were able to model the girders, and we did, of course, for all the spans. Inside the first span, if you have a look, we have a cross frame, and this cross frame you can see. We can see. I will just remove the names here, so we will have better visualization. We can remove all these things by just checking the checkboxes that we have on the right side, and we can remove all the things that we don't want to see. And if I also remove the station points and station values, and I think I have here, and I want to remove also this tendons, which I don't need. Then once we remove the things that we want to visualize or render, we can have a look, a better view of what's happening here. So here, what's really happening is that also we have, okay, cross frame web here, which is defined like this. Here we have a cross frame shape web defined like this, and we have the plate defined also like that. And once we define them, so we can place them. So we place, okay, this element from this point to this point, and if you click this one, you can see it's a girder, it's a cross frame girder, and it's called 101. So we have cross frames. You can see 101 plate 1 here and plate 2 here. So we define all this first as cross frames. Then once we define the plates, we can define the webs as well here. So we have web 1, web 2 here, and we have web 3 here. So we can define those and place them. Of course, when you place these webs, as you can see here, if I just, for example, click on the web one here, the one that we have clicked, when we have here a setting where we can change the length offset. So how far away from this do you want it? So if I say I want to have, for example, 0.5 and also 0.5 here on both sides, and recalculate everything, and we can zoom in here, you can see the plate, this plate has an offset from the point that we want to place it. So basically we can also do such things, and we can navigate, or we can manipulate the placement or the shape. So once we have, of course, the girders and the link girders defined and so on, we focus on the creation of the abutments. So the abutment, usually when you create a link girder, you need to start with the abutment, or when you create a girder bridge, you start with the abutments or the substructures. So because these substructures are the guiding, or the guiding for the length of the girders and for the position of the girders. So besides this link girder we go to the bodies, where in these bodies we have different elements, as you can see, defined on all these elements are based on a template, and this based on the cross section, and this cross section has basically it's based on a free parametric modeling. So we can do this, and we can basically model the abutment. So the advantage here is that, okay, for elements that you create with the free parametric modeling, you can of course reuse them later by partially exporting them and importing them back into the project. Of course, also you can introduce any kind of change to the parent object. Maybe if it's this wall that we have, and once you change this wall somewhere, the height, the thickness, or the position, and everything will also move. So basically we have an overall integration. So basically this seems the project which has the best of everything, where we use the axis-based modeling to model the decks at the top, and we use the Link-Girder to model the girders and the cross frames, and we use the free parametric modeling to model the abutments. And of course, the piers are also modeled using the classical approach, where we use a template, and from the template we create the object. So this brings to the end of the webinar. Thank you very much for your attention. Thank you.